Hey everyone, and welcome back to another explainer. Today, we're diving into what is honestly one of the most fascinating leaps in modern tech. We're going to explore how artificial intelligence went from just understanding the words we type to literally dreaming up entirely new, complex visual worlds. It's a wild ride, so let's just jump right in.
So, here's the big question framing our whole journey today. We've successfully taught AI to speak, right? But how exactly does it learn to see? And, even crazier, how does it learn to create? I mean, predicting the next word in a sentence is one thing, but teaching a machine to understand a photograph, let alone paint a masterpiece totally from scratch, that's a whole different universe of complexity. To really get how we arrived at modern AI art, we first got to understand the basic building blocks of machine vision.
You know, when most of us hear generative AI today, text is usually the first thing that pops into our heads. We think of language models, like GPT-2, taking in text inputs and churning out text outputs. And honestly, it makes perfectly good sense. In the public eye, we've been super focused on this kind of text generation. These language models are fundamentally trying to model human language, and they do a fantastic job of it. But if we want to talk about generating images, well, we have to look completely beyond natural language processing. Way before the massive craze of text-based models totally took over, there was another field dominating the deep learning landscape. That field is computer vision. Because, think about it, if we want an AI to generate an image, it first needs to actually understand what an image is. So while language models are obsessing over the structure of words, vision models are focused entirely on interpreting and classifying visual data. We aren't just handing the AI a file and saying, hey, this is a picture. No, we're asking it to meticulously analyze thousands of individual pixels and figure out exactly what's hiding inside that frame. Is it a cat? A dog? A little yellow duck?
Let's actually walk through the evolutionary steps of computer vision to see how this works. It starts with basic classification. The model just spits out a simple label, like cat. Okay, cool. Then comes classification with localization. Now, not only does it know it's a cat, but it draws a neat little bounding box right around where the cat is located. But real life is messy. There's rarely just one thing in a picture. So we step up to object detection, where the model spots multiple distinct objects in a single scene and draws separate boxes around all of them. And finally, we reach the absolute pinnacle. Instant segmentation. Goodbye, clunky boxes. Here, the AI perfectly outlines the exact pixel boundaries of every single animal. It knows exactly where the dog ends and the grass begins. It's incredibly precise.
All right, moving on to Section 1, Enter the GAN, the art forger and the detective.
Once AI mastered analyzing images that already existed, the natural next step was, of course, creation, generating a brand new synthetic image completely from scratch. And this brings us to a really revolutionary architecture, the Generative Adversarial Network, or GAN for short. Let's break down the two opposing players in this massive mathematical game of cat and mouse. On one side, we've got the generator. Think of this as our art forger. Its entire job is to create fake synthetic data out of thin air that looks as realistic as possible. On the exact opposite side, we have the discriminator. This is our detective. Its job is to look at data and make a call. Is this a real image from our actual data set, or is it a clever fake whipped up by the generator? They are locked in this constant, fierce, adversarial battle.
Now, behind the scenes, this whole game is driven by a pretty heavy mathematical concept called maximizing log likelihood. But don't let the math scare you. Just think of it as the ultimate scorecard. The discriminator, our detective, outputs a probability showing whether it thinks an input is real or fake. It wants to maximize its score by correctly labeling real data as real and catching the fakes. Meanwhile, the generator is doing everything it can to maximize its own score by getting its fake data classified as real. It essentially wants to maximize the chances that the discriminator messes up. And because they're constantly trying to outscore each other in this high-stakes match, the AI actually learns to generate astonishingly realistic images.
Up next, Section 2, Modern Magic, Cycle GANs.
Okay, the sheer magic of a cycle GAN lies in something we call unpaired image-to-image translation. Usually, to teach an AI to translate something, you need exact, perfectly matched pairs. But cycle GANs? They allow transformations across completely different domains without needing paired training examples at all. It's wild. We can take an image of a regular horse just running in a field and instantly translate it into a zebra. We can take a bright, sunny summer landscape and turn it into a freezing winter scene. We can even take a standard photograph and translate it into a painting that looks exactly like a Monet or a Van Gogh. This architecture is the invisible engine powering so many of the advanced AI style filters we mess around with today.
But wait, how does the AI actually know it's making a zebra out of that specific horse, and not just spitting out some random generic picture of a zebra? Well, it relies on a brilliant stabilizing mechanism called cycle consistency loss. Basically, this ensures that an image translated from one domain to another, say turning our horse into a zebra, can be translated back, and the final result has to remain absolutely unchanged. So if the AI turns your horse into a zebra, it is mathematically forced to prove that it can perfectly reconstruct your exact original horse from that new zebra image. This is totally crucial because it keeps the model grounded. It's exactly what stops AI image filters from just completely losing the original context of your photos.
And to actually pull this whole thing off, a cycle GAN uses dual GANs, meaning it doesn't just use one generator and one discriminator. No, it uses two entire separate GAN systems to learn the mapping between the two domains in both directions. One GAN learns how to turn horses into zebras, while the second GAN focuses entirely on turning zebras back into horses. By working together in tandem, they ensure absolute consistency and super high-quality image generation both ways.
Finally, Section 3, wrapping up.
We've covered some seriously dense but incredibly fascinating terrain today. First, we saw that generative AI goes way beyond the text generation we play with on our phones every day. To generate visuals, we first had to conquer computer vision, moving from just labeling an image to precisely segmenting out every single individual object. Then, we explored the revolutionary engine behind image generation, GANs. We saw how that constant mathematical battle between the generator, the forger, and the discriminator, the detective, literally forces the AI to produce stunningly real data. And finally, we looked at the modern magic of cycle GANs, and how combining dual GANs with cycle consistency loss lets us flawlessly translate horses into zebras and summer into winter.
All of this leaves us with a truly exciting thought to ponder. If we've successfully taught machines the crazy complexities of human language, and we've now taught them to expertly analyze, segment, and generate entirely new visual worlds right out of thin air, what medium will generative AI master next? The pace of this technology is just staggering, and the possibilities are absolutely endless. Thank you so much for joining me for this explainer. Keep learning, keep questioning, and I'll see you next time.